This video is going to show you how you can use the SPI protocol to shine an LED rainbow from your Android Things application. We'll discuss the Raspberry Pi Rainbow hat and its actuators, in this case the 7 RGB pixels, which we'll use to make a lovely kid-style rainbow coloured pattern. Let's get started. SPI stands for Serial Peripheral Interface. This can be used for communicating to one or more peripherals quickly over a short distance. You talk to a master device and this communicates with each slave peripheral connected to it. With Android Things, you connect to each slave peripheral separately, hiding most of the complexity. Our Raspberry Pi is now plugged in and connected via ADB ready for development. We have the Rainbow hat connected to the top of our Raspberry Pi. This hat has a lot of peripherals, and amongst them the APA102 LED strip. We are going to code our app so that the LEDs shine a kid's colours rainbow. The LED strip is located across the top and across the middle of the Raspberry Pi. When working with the Rainbow hat, we can see how each of the peripherals on the hat is connected to our Raspberry Pi by looking at the pinout diagram. In this case, we can skip that step, as here on the back of the Rainbow hat, it shows the APA102 LED strip is connected on SPI 0.0. Let's remember that for later use. To understand how each peripheral works and determine the protocol needed to talk to it, we should consult the Rainbow hat documentation and, if needed, the specific peripherals datasheet. In the documentation shown here, we can see the LED strip described as the 7-element APA102 Rainbow, and it says it is connected via SPI 0 and with chip select CE0. This is the hint we need to tell us to use the SPI protocol for our communication. Remember, we read SPI 0.0 on the back of the Rainbow hat. This matches the SPI 0 chip select 0 that we see here. If there were multiple slave peripherals connected to this SPI interface, they would be called SPI 0.1 and SPI 0.2, etc. The documentation also explains the data format for writing to this peripheral. We'll refer to this later on, and for now it means we don't need to look for a datasheet, everything we need is here. Okay, let's program the LED strip. Here I have an Android Things project already set up in Android Studio. If you aren't sure how to get your project to this point, you can revisit the previous first app lesson for instructions. First, we create an instance of Peripheral Manager Service using this code. This is the Android Things SDK class that allows us to open connections to different board pins using the different available protocols. Using this instance, we want to open an SPI connection with the pin address we saw earlier on the back of the board. When we open this connection, we're given back an SPI bus variable that will now allow us to communicate using the Android Things SDK SPI class. We'll use this variable in multiple Android activity lifecycle methods, that's why we make it a field. Notice that we have to wrap the open SPI device call in a try-catch block. This is because the method, and most other methods we will use in the future, all throw a potential IO exception. This is due to the fact that we are dealing with hardware, and at any moment the pin or the peripheral could become unavailable, for instance because of a loose wire. At that point, calling the method will throw this exception. We are assuming that all our wires are nicely connected, and if we do get one of these IO exceptions, it would be really bad for our app, and actually we want to crash straight away, so we can diagnose the problem as soon as it happens. That's why in the catch block we throw an illegal state exception, as we are not expecting nor wanting this to happen. This is known as failing fast and is a clean code best practice. The benefit of this is our bus variable is either a fully instantiated field at this point or our app has crashed. Therefore, from this point on, there is no need to check if our bus field is null, it never is. Opening a connection to a pin is capturing this pin as your resource, and like with all resource management, it is good practice to release resources once you are finished with them. Also, if we have an open connection to a pin, no other code can open a connection to that pin until we close our connection. Since we open the connection to our pin in the onCreate method, we should use the symmetrically matching pair from the Android lifecycle to close the connection. Therefore, we close the SPI bus connection in onDestroy using this code. Again, close can throw an IO exception. We can't do anything about this if we get an exception, but we can log it out so that we know next time our app starts if something unexpected had happened in the past. With SPI peripherals, there are 3 attributes that make up the mode of communication. Setting the mode is important for correct data transfer. They are the idle level, leading edge, and trailing edge. The combination of these 3 choices make up the mode. I actually couldn't find documentation of the mode or these attributes described in a simple terms for this peripheral. Therefore, to keep things simple, I found through trial and error we will use mode 2 for communication. You can also set the frequency of communication, the endianness, i.e. if the bytes should be read forwards or backwards, and the number of bits per word. For all 3 of these, the default value works for our device, so we'll just keep it with those. Now we have our SPI peripheral configured and ready to show our rainbow. Let's write some data into it to turn on the LEDs. We'll do this in onStart to keep a separation from the onCreate configuration code. Our LED strip takes RGB values for each of its 7 LEDs. I have created another class here called Color and set up an array of 7 colors that will make up our rainbow. Now we are ready to sing a rainbow in the main activity. First step, we'll be using the write method of the SPI Bus API. This allows us to send a byte array of any length we need for our data. Here is the code. Looking back at the documentation, we can see the data format for communicating with the LED strip. The documentation explains that we will need a 37 byte update transaction. So let's create that as our data array. It looks like this. Next is a start frame of 32 bits. Each byte is 8 bits, therefore 32 divided by 8 is 4. We need 4 bytes of 0 bits. Let's do that in a simple loop with this code. The docs then say to send the data for each of our 7 LEDs in the strip. Each LED requires 32 bits, which is 4 bytes. First byte is the start frame plus the brightness, then 1 byte each for blue, green and red in that order. For the 7 LEDs, let's create a loop like this. Now we are going to have a fixed brightness of 3, so let's create that byte, combining it with the start frame byte as a constant with this code. Each color segment of blue, green and red is going to take its color from our rainbow constant I showed earlier. Using this in the loop and assigning blue, green and red to each byte looks like this. Finally, the doc says it needs an end frame of at least 36 bits. 36 divided by 8 rounded up is 5 bytes. So we loop for the final 5 bytes, setting them all to zeros with this code. We've created our 37 byte update transaction, and remember, we are writing it to the SPI Bus API write method. Let's run our app and check the rainbow hat to see the APA102 LED strip shining a beautiful rainbow. That's it. You now understand how the Android Things SPI output communication with peripherals works. You can interface with an APA102 LED strip controlling each LED's brightness and color individually but updating simultaneously. This knowledge also transfers to other SPI peripherals such as other types of LED strips, pressure sensors, potentiometers, or graphical displays.